Welcome to Maths with Bob. Today we're looking at polynomials, and in particular we're looking at the relationship between the roots and the coefficients. And hopefully we have seen this before, alpha plus beta equals minus b on a and all those ideas. But if you haven't seen these before, but basically the roots and the coefficients are in fact related, and there is a general relationship. This one here, I'll just see if I can actually hold on, let's see if we can. Okay, now this is quite a complicated expression, which just basically means that we've got an alternating sign of the roots, and we have to take them what's called r at a time. Now this concept of taking the roots r at a time sometimes is a little bit complicated, but we'll go through a few examples and try and explain what this means. Okay, so basically what does it mean? Well, firstly, as you can see here, it means that the zeros are actually in combinations with the coefficients. And just have a quick look. Normally, we would write a polynomial with a, b, c, d, okay, e, f, g, etc. And you can see here, I've actually looked at the first instance, which is I'm taking the roots one at a time. Now, obviously, if I take the roots one at a time, that's like you can see here. I've actually, if you here, you can see here sigma alpha I equals minus b on a. That just means the roots are actually taken one at a time from 1 to n. Now n is obviously the degree. Now you can see here, depending on the degree, that will indicate the number of roots we need or we have, because we know the fundamental theorem of algebra says that we have at most n roots to a degree n polynomial. Anyway, degree 2, we know that we have alpha 1 and alpha 2, which we normally write as alpha and beta. Okay, the Greek letters come in into a big way in here. Okay, so we have alpha plus beta is equal to minus b on a, and you can see here if the degree is 3, we go sigma alpha I of 1 to 3, which gives me alpha 1, alpha 2, alpha 3, which we normally write as alpha beta gamma, and that's still minus b on a. So it doesn't matter what degree we have, basically. The sum of the roots will in fact be always minus b on a. Let's try sum of the roots taken 2 at a time. Okay, here we have the sum of the roots taken 2 at a time. You can have a quick look here. You can see here that we have alpha I, alpha j, where I is not equal to j. So that basically means we don't have alpha, alpha, and beta, beta type things happening. Okay, so we now got to take the roots, if you like, as a combination. So we're taking 2 from 3. Okay, so we are now, if you see here that we have if the degree is 2, the number of ways I can actually take 2 from 2 is actually only 1. So we actually say that if it's a degree 2, like a quadratic equation, then the sum of the roots taken 2 at a time is actually equivalent to what's called the product of the roots. Okay. Now, if it's a degree 3 polynomial, then you can see here 3c2. There's 3 combinations, and you have a quick look there. Alpha 1, alpha 2 plus alpha 1, alpha 3 plus alpha 2, alpha 3. And we normally write that in terms of the Greek letters alpha and beta and gamma. Okay, you can see that's equal to c on a. Okay, if the degree is 4, okay, you can see there's 6 combinations, 4c2. And we have alpha, beta, gamma, and delta. Okay, so we get a bit more complicated. Okay, let's have a look at the roots taken 3 at a time. Now, obviously, we need to start off degree 3 because we can't actually take 3 roots from a degree 2 equation. And so we have to start at degree 3. And obviously, at a degree 3, 3c3 is 1. So in terms of a degree 3 or a cubic equation, obviously, the sum of the roots taken 3 at a time would in fact be the product of the roots, which is minus d on a. This is the, you can see here, the oscillating sign, plus, minus. That comes from the original expression. Okay, so if it's degree 4, you can see here it's 4c3, there's 4 combinations. Okay, we can see alpha, I've just all written it down here, alpha, beta, gamma, delta. Okay, degree 5, we need to go into the epsilons, and so on, basically. So it gets a bit more complicated. But basically, what's happening is there is, in fact, obviously, a relationship between the roots and the coefficients in a polynomial equation. Now, what usually happens, I'll just try and get, oops, we're trying to, okay, here we are. So if we have actually, a polynomial equation with the roots, alpha, beta, gamma, delta, etc., and we want to create a new equation which is based on the original roots, alpha, beta, gamma, delta, etc. Okay, so we then need to do a little bit of a manipulation, or if you like, a substitution into the original polynomial, and we need to try and work out how we do this. And if you look at, I always use what's called the big X, little x idea, where you actually look at the pattern, like 1 on alpha. I'll just look at the examples down here. We've got this polynomial 2x cubed plus 3x squared plus 4x minus 1. Okay, so we need to form a new equation with the roots 1 on alpha, 1 on beta, 1 on gamma. Okay, so obviously it's a degree 3, you can see here. So you can see that really I've got the reciprocal of the roots. Okay, so I say just the new polynomial variable big X is equal to 1 on the little x, the little roots. Okay, and then we rearrange this to make a little x the subject, which you can see here is 1 over big X, and then we create what's called P of 1 over X. Now, if I want to find the one with the squares of the roots, alpha squared, beta squared, gamma squared, you can see here big X is equal to the little roots squared, and I make X the subject. Okay, X is equal to root X. Okay, these would be positive alpha squared, beta squared, and gamma squared. So I create what's called P of root X. Okay. I'm going to go through an example in a minute of this last one where it's 1 over alpha squared plus 1 over beta squared plus 1 over gamma squared. You can see here big X is equal to 1 on the roots squared. Change the subject to obviously back to little x. And you can see here I'm going to need to create a P of 1 over root X. Okay, so let's actually see how we do this. Okay, so I now need to create what's called P of 1 over root X. And actually that's x to the negative 1/2. So I need to, if you like, substitute x is equal to big X to the negative 1/2 into the original polynomial P of little x. And you can see here, when I do that, I'm just going to rewrite it as 2 over x root x plus 3 over x plus 4 over root x minus 1. Now, okay, what we do now, I mean, we're going to have to try and get rid of these root x. So I create a common denominator, put it all over x, this is big X root big X, okay, and then multiply throughout by x root x, and you can see here we end up with, basically let's just highlight where we are getting to. We're getting to here. Now, this is basically where we're getting to. Now, this is 2 plus 3 root big X plus 4 times big X minus x root big X equals 0. Now, you can see here we've got a root x in this equation. We need to eliminate this. So all we do, if you can see here, we just put the root x's together, factor out a root x, and then we square both sides. We're going to square both sides. You can see here what happens when we square x minus 3 root x. Obviously, we're just going to get x minus 3 squared, which is x squared minus 6x plus 9 times x. Then we have to square the 2x plus 4. Okay. Now, you can see here when we actually eventually get down to here, we have x cubed. Okay, we've got an equation. We just have to move everything over to one side. And then we get down here at the final part here. This is our new equation. Okay, so this is P of 1 over root big X, which is in fact, okay, the polynomial equation now, which has roots related back to the original polynomial. Okay, and these are 1 over the roots squared. Okay. And you can see here, this is x, capital big X cubed minus 22 big X squared minus 7 big X minus 4 equals 0. Now, all we do is just obviously drop that big X down to the small x, and we now have the new polynomial equation, which is not that difficult. But it is a little bit tricky to actually create these new polynomials with the patterns, which you need to examine and try and find a pattern and do the substitutions. Okay. Well, look, thank you for watching, and bye for now.